This building does not look like a power plant, but it may soon consume electricity like one. Behind these walls, thousands of machines turn electricity into computation, and computation into heat. Every AI prompt, every model training run, begins with something physical moving through copper. The internet once felt weightless. The AI era is making it brutally heavy. Inside the servers, electricity becomes heat almost instantly, and that heat must be removed continuously. That is why an AI data center is not just a building full of computers. It is a power distribution machine wrapped around computation. The servers are only one layer. Around them sits an entire industrial support system. And as AI grows, that support system is colliding with the limits of the grid. The question is no longer whether AI can scale. The question is whether the grid can feed it. Because the real AI race is not only about chips, models, and code. It is about substations, transformers, cooling systems, batteries, backup power, and the hidden machinery beneath intelligence. To understand the problem, start with the basic unit of data center growth, electrical load. A small facility may use a few megawatts. A major AI campus can demand hundreds. When multiple campuses cluster together, the request can begin to approach grid-scale territory. Modern AI racks are denser, hotter, and far more power-hungry than older server rooms. The more computation packed into each rack, the more heat engineers must control. The power path begins outside the building and ends deep inside the rack. First, high-voltage electricity has to reach the site through transmission infrastructure. Then a dedicated substation steps that power into a form the campus can use. Transformers become one of the most important machines in the entire AI supply chain. Inside the electrical rooms, switchgear routes power and isolates faults before they spread. UPS systems create a short protective bridge when the outside grid flickers or fails. For longer outages, many campuses rely on large backup generator farms. But electricity is only half the story. The other half is removing heat. Airflow must be controlled carefully, or efficiency collapses and equipment temperatures rise. As rack power climbs, liquid cooling becomes less optional and more like infrastructure. Engineers measure this with efficiency metrics that compare computing power to total facility power. A true AI campus is not one building. It is an energy campus. It needs land, power access, cooling access, fiber access, and room for future expansion. In some regions, water and heat rejection become as important as electricity. Before construction begins, the project still has to win a place on the grid. This is where the blueprint stops looking digital and starts looking like heavy industry. At MegaScale, artificial intelligence begins to look less like software and more like urban infrastructure. The central engineering problem is simple to describe and difficult to solve. How do you feed a machine that grows faster than the power system around it? The execution starts at the edge of the transmission system. Power arrives at high voltage, where breakers and protection systems control the first handoff. Transformers then reduce voltage while carrying enormous current into the campus distribution network. From there, medium voltage feeders branch toward electrical rooms across the site. Main switchgear decides where power flows and what gets isolated during a fault. Protection relays watch the system in milliseconds, because failure cannot be allowed to cascade. Redundancy is built everywhere, with alternate paths ready before the first path fails. The UPS layer protects the servers from voltage dips, outages, and switching events. If the grid blinks, the computers should never notice. Battery cabinets provide seconds or minutes of protection, buying time for backup systems. If the outage lasts longer, backup generators are designed to take the load. At large campuses, backup generation can become an infrastructure project of its own. Automatic transfer systems coordinate the shift without interrupting critical loads. Inside the data hall, power is stepped down and distributed to individual rack rows. Overhead busways allow dense rack rows to receive power in a controlled, modular way. Every rack becomes a tiny endpoint of a much larger electrical chain. The processors perform the computation, but almost all their electricity eventually becomes heat. Cold air or chilled liquid must reach the equipment at exactly the right rate. Hot air must be captured quickly before it mixes back into the cold side. In high-density AI rooms, liquid cooling can move heat more efficiently than air. Heat exchangers separate the computing environment from the larger cooling plant. Outside the data halls, chillers and pumps become part of the computation system. The heat finally leaves the campus through towers, radiators, or other heat rejection systems. Thermal control is not secondary. It determines how much computing the campus can safely run. Power quality also matters because sensitive electronics need clean, stable electricity. Large electrical systems may need filters, reactors, and capacitor banks to protect voltage quality. The grid must supply not only real power, but also voltage support and stability. A control layer monitors every major system and coordinates responses faster than operators could manually react. At this scale, engineers need a live model of power, temperature, and risk. The goal is not just to prevent failure. It is to survive failure. A well-designed data center should ride through disturbances without dropping its critical load. But the grid around the campus still feels the weight of that demand. AI demand can ramp faster than utilities can build transmission, transformers, and generation. That makes transformers and substations some of the most valuable bottlenecks in the system. One data center is a major load. A cluster of them can reshape an entire region. Utilities must decide where to reinforce the grid before the next wave of demand arrives. At full scale, the data center becomes less like real estate and more like an industrial power plant. The hotter the environment, the harder the cooling system has to work. Cooling equipment can become a major part of the total electrical demand. In water-stressed regions, heat rejection becomes a planning constraint, not just a mechanical detail. Backup systems also need fuel, testing, maintenance space, and strict safety design. Some campuses add batteries to reduce peaks, bridge outages, or support the local grid. Others explore on-site generation when the external grid cannot deliver enough capacity quickly. Clean energy contracts can help, but contracts do not remove the physical grid problem. Data centers run all day, even when the rest of the grid reaches peak demand. If too many large loads cluster together, congestion appears before new wires can be built. This is why AI growth is becoming one of the biggest grid planning problems of the decade. The deeper lesson is that AI is no longer only a digital technology. Every digital breakthrough now depends on physical systems that are slower and harder to build. To serve AI, regions may need new substations, new transmission, and new power sources. The limiting component may not be the server. It may be the transformer. Substation expansion is becoming part of the AI infrastructure race. Smarter controls may shift workloads, smooth peaks, and reduce stress on the grid. Instead of one overloaded cluster, the future may require more distributed computing geography. The answer may involve renewables, storage, nuclear power, gas backup, and stronger transmission together. Future data centers may need to support the grid, not merely consume from it. The hidden machine behind AI is made of copper, steel, silicon, coolant, and control software. Even when power exists on paper, permits, corridors, and local grid capacity can slow deployment. AI infrastructure depends on two networks arriving together, fiber for information and power for computation. The campus expands in modules, but every module adds electrical load and cooling demand. Resilience becomes essential because digital services expect uptime even when the grid is stressed. The machine is intelligent only because a much larger physical machine keeps it alive. The future of intelligence may depend as much on grid engineering as on algorithms. At MegaScale, the question is not only how smart the machine becomes. It is whether the power system can survive it. And until the next build, this is MegaScale Engineering, where we break down the machines too large to fit on a blueprint.